Assalamualaikum and good day everyone. Today we're going to continue our class with chapter 4, linear transformation. Okay, chapter 4 we have four main things here. We will start with mapping and the properties of linear transformations, null space and its range, and then we will look at the sum of the theorem. We will start with mapping. Define that mapping of T from V, which is a vector space, to W, also a vector space, as TV, T, V to W here. T comes from transformation, okay? This is standard terminology for such functions. I think in your discrete class, discrete mathematics, you learn about, the fx equals to what? Same as here, but this is transformation from vector v to vector w. Vector v, let's say r2, then it will transform to r4, or maybe r2 transform to still r2. Okay, doesn't matter, but it is transformation from vector space v to vector space w. Alright, so v is called domain of transformation T, and w is called codomain of T. I think if you, like I mentioned before, see in your discrete class, let's say this is your v, this is your w, right? So inside here v, this is the domain, right? This is the codomain. I think you're already familiar with the term. So this is v, this is w, and v transform to w, pointing into the codomain of the transformation. If v is in the v and w is in w, okay, like we draw here, we can say that transformation of v is equals to w, same as if you learn about function before in your discrete mathematics. Then the w then w in called the image of v under t. So this is image, and the set of v in v such as the t v equals w is called the pre-image of w. This is the pre-image. Okay, if they say they want the image, they want the things here, but pre-image is the one before the transformation. Okay, for example 1 here, we see the questions define a mapping T R2 to R2 by, this is the transformation that we have. Okay, find the image of the coordinate vectors E1 and E2 under the mapping of T. Alright, this is not a linear transformation yet. As linear transformation, we will have some condition that we need to satisfy. We will learn later. But this is just a mapping transformation. Okay. So as I mentioned before, this is the v, this is w, right? From transformation of v to w. So R2. So we know if R2, this is R2, right? This is v. And then after transformation it becomes w. We still, let's say, AB, which is also R2. Okay, this is R2. So this is the transformation that they give to us. Txy is equals to x plus y, x minus y. Now find the image. Find the image is find the after the transformation, right? Okay. We see at the first vectors here, E1, 1, 0. So since E1, 1, 0, E2, 0, 1, we try to solve the first one first. TE1, transformation of E1 is equals to, see this transformation here. If you remove the T, it will be this equation. So what is our x? What is our y? X is 1, y is 0, right? So x plus y. And then looking back here to the transformation, we have the second row here, x minus y. So we get x1 minus 0. So after that, you will get your 1, 1, which is the image w here, alright, which is still in R2. Okay, what about the E2? 0, 1, same, this is your x, this is your y. If you look back to the transformation here, txy, so you will get t of this one here, te2 is equals to x plus y, 0 plus 1, and x minus 1, 0 x minus y, 0 minus 1. So you will get, this is your image for E2, still in R2. So we can see this based from the questions. Okay, some of the other question will give you other transformation that you need to map, but for this question, this is the mapping, the transformation. So you need to take the v that they give to you and then find out what is the transformation that they want you to do. This is based on the question. So you solve it, then you get your image. Okay, for let's say for this question, E1 and E2, you see we have different vector here. 1, 1, 1, negative 1. Okay, now example 2. Now they ask you two things for example 2. So we start with the definition here. For any vector v, v1, v2 in R2. So the transformation is still R2 to R2, right? Defined by transformation of v1, v2 is equals to v1 minus v2 and v1 plus 2v2. So the first question, find the image of v. V here is negative 1, 2. So this is your v1, this is your v2. Alright? So basically it's the same as before, previous example. So we just change the value here. So t negative 1, 2, this is your v1, v2, right? Is equals to this equation, v1 minus v2 and v1 plus 2v2. So you insert your v1 and v2. Negative 1, negative minus 2, negative 1 plus 2 multiplied by 2. So you will get your, this is your w, your image. Okay, for this v. Okay, straightforward, same as what we do in the previous example. Now, what about b? Find the pre-image of w. So they give you the pre-image. They give you the image here, w. Before this, they give you the pre-image, right? Now they give you the image, negative 1, 11. So as you know, as I mentioned before, this VW here. So you have your V and W. Now before this, they give you V. You need to find after the transformation. Now they give you W. They want you to find what's the pre-image of your image. So how can we do? We know that if the transformation of V is equals to, this is the how you calculate the W, right? So this is equals to your W. The transformation of V is equals to this. This is how to calculate your W, but they give you the W already. So you need to equal to negative 1, 11. So negative 1 here is how you calculate it by solving this, and 11 is by solving this, right? So you separate it into row here. V1 minus V2 is equal to negative 1. V1 plus 2V2 is equal to 11. So you solve the linear equation. When you solve the linear equation, you will get this unique solution for V1, which is 3, and V2, which is 4. So this is your V for the image of -1, 11. -1, 11. This is the V that you need to find. Okay. So the pre-image of -1, 11 is set of R2 consisting of single vector 3, 4. Alright. The difficulty of this type of example depends on your formula. If formula is quite hard, then it's quite hard for you to find a unique solution. But for this type here is quite straightforward, so you can just change into the linear equation and find your V, the pre-image. Okay, now we go to the definition of a linear transformation. Before this, we just do a mapping between vector spaces. Doesn't mean that it is a linear transformation. Okay, the mapping of T between vector spaces that satisfy the two properties here, 1 and 2, when it satisfies both, then it is called a linear transformation. Okay, before this, what we've done, we just do a mapping. Okay, but if the mapping satisfies these two properties, then it is called a linear transformation. Okay, let's look at the first one here. Let's say you have UV, right? You have your vector spaces to here. For this, you have U plus V first in the first vector space, right? W. And then you transform here. After you plus, then you transform. Okay? For this one, let's say the same thing, you have VW. You have your UV. You bring it here first, TU, TV, then U plus V. Means that it happens on W. This one, it happens in V. Okay, so the transformation U plus V, then we get into W. But for this one, you transform it first, then U plus. Okay, so this one happens, this transformation happens in V, transformation of U plus V. You plus it first, and then you transform it. For the second one here, you transform it first, then U plus. And it must be the same, must be equal to. This must be equals to this. Then you can say that it is a linear transformation. Same here. If you see the second one here, let's say you have again VW, right? So you have two vectors here. So here CU, then you transform the CU. So you transform the multiplication. You multiply first, then you transform it. But for the second one, VW, so you have your U, you transform first, then you multiply. Okay, so it happens on W. The first one, the multiplication happens on V, same as your plus. Your plus for the first one here, the plus happen on V, and then you transform the plus, the addition. But the second one, you transform first, the addition comes after transformation. Again, for the multiplication, the first one, you multiply first and then you transform. But for this one, you transform first and then you multiply. And again, it must be equals, means that must be the same between these two in order for it to be called linear transformation. Okay, this is the two properties that make the mapping called a linear transformation. Before this, what we have just done in previous example is just a mapping. Okay, this is the properties that make it a linear transformation. Okay, now we look into example 3. Example 3 asks us to show that the transformation of v1 v2 is equals to v1 minus v2 v1 plus 2v2 is a linear transformation from r squared r2 into r2. So we have transformations from r2 to r2. Okay, and we know that we have two properties to fill if we want to show that it is a linear transformation. The first property is the addition, right? So we will have transformations from u plus v must equals to transformation of u plus transformation of v. We already know from our discussion of the properties before. So here we know that we must have u, which is, let's say, u1, u2, and then you have v, which is v1, v2. Alright, because we want to solve there, I want to see about the properties. So once we have this, we need to know our u plus v, which is u1 plus v1, and then u2 plus v2. Okay, then we need to find the transformation for these two, transformation of u1 plus v1, u2 plus v2. So you will get your answer u1 bracket of u1 plus v1 minus your u2 plus v2. Then we have your second one, u2 plus v2. Here will be u1 plus v1, u1 plus v1 plus 2u1, okay, 2u1, sorry, it's supposed to be u2, 2u2 plus our v2. Look back at the example they give you here, u2 plus v2 here, because you want to transform, right? So this is your transformation of u plus v, u1 plus v1, u2 plus v2, and it's equals to, this is the transformation. So your v1 is this one, u1 plus v1 minus, remember, minus u2 plus v2, because this is your v2 here. And then second one, v1, so you take your v1, u1 plus v1 plus 2 u2 plus v2. Okay, then you will get your answer u1 plus v1 minus u2 minus v2. Don't make mistake here, okay? And then you have your second one here, u1 plus v1 plus 2u2 plus 2v2. Okay, this is your answer. Right? This is for the u plus v. Then we need to solve on the transformation first. This one, transformation of u, transformation of v. And we want to see whether it is the same or not. Same as the answer we get here or not. You can write down again your u, which is the same here actually, but for the sake of the example, we try to do it. When u2, v, v1, v2, and transform this. Transform this, you must write in this transformation. So it's equals to tu is equals to u1 minus u2, and then you will have u1 plus 2u2. As for the V, same, you will get your V1 minus V2, V1 plus 2V2. Remember where I got this equation is from this T that they give you here. Alright, this is your V1, V2. So U1, U2, U1 minus U2. And then the next one is V1 plus 2V2. So this is your U1 plus 2U2. And then you do it again for your V. Alright, now we need to find the addition between the transformation of U and transformation of V. These two. Alright, so what answer do you get? You have your U1 minus U2 plus your V1 minus V2. And the second one you will have U1 plus 2U2 plus your V1 plus 2V2. Then you have your U1 plus your U1 plus your V1 here, make it easier, minus U2 minus V2. And then for this one you will have your U1 plus V1 plus 2U2 plus 2V2. And then we check back the answer. Is it the same? This one and this one, is it the same? Because remember, we need to fulfill this addition, alright, the addition properties. So we have the same answer, right? U1 plus V1 minus U2 minus V2 okay. The second one here, you have U1 plus V1 plus 2U2 plus 2V2. So it is the same from both. So we can say that one of properties already done. But of course, for linear transformation, both must be satisfied, the addition and multiplication. Now we need to look at the multiplication. Okay, this is still for addition. Besides what I've done before, right, where we compare one by one, we can also use this type of methods here where you just find the following, where you find the following of U plus V here, and then you just solve equals the transformation of U plus V, and then you prove it whether it is TU plus TV. This is much more simplified method, but I think some of you may get confused, right? If you feel confused, feel free to use what I have done before in previous slides, where I do one by one. I try to solve it U plus V, transformation of U plus V, and then I do the transformation of TU plus TV. It's longer than this, but I think maybe if you are confused, you can use that way first. Then if you have more adaptability, then you can understand better. You can use this type of solution where you can see here, same as our TU plus V, they put our TU U1 plus V1 and their V U2 plus V2, and then they try to solve this equation by transform it into this form. So same as I think the first one we do, but this one they try to prove directly it is TU plus TV. So this is our U, and this is our U, this is our V, this is our V, right? So U1 plus V1 minus U2 plus V2, this one, and then U1 plus V1 to U2 plus V2, which is this one, and then you simplify it. Okay, you change the U's to your U's. This is the U's and this is the V's. Alright, and then this is also same, this is the U's and this is the V's. Then you try to move the U here into the U's, and then the V into the V's, the V here. Okay, so you get U1 minus U2, U1 plus U2, and then you have V1 minus V2 and V1 plus 2V2. So here you can say that this is actually transformation of u. If you just transform u, right, so you have u1 plus minus u2, u1 plus 2u2. If you just transform u, you can look back at our previous slide, and this is just our transformation of v. They can say it is a transformation of v, where v1 minus v2, v1 plus 2v2 is the same if you just transform it. You can look at the previous slides. Okay, this way they prove directly. Okay, they don't need to compare the last answer, but what I've did before, if we compare the last answer, if it's the same, then we can say it is a it satisfies the properties. Both is correct. It's up to you guys which one that you want to use. All right. Okay, now we have come to the multiplication part, where we multiply a scalar to the u. So we have our u here, u1, u2, and then you have cu1, cu2, right? So we need to multiply them. We know that our t you can multiply first should be the same as the scalar when you multiply first, then you transform. Should be the same as when transform first and then you multiply. All right. So we try to prove. They give you the solution here, where same as in the previous one. They try to solve directly, where you multiply first and then transform is equals to you transform first, then you multiply the scalar. Okay, so we have here t cu1 cu2 they give you, and then you multiply them with the transformations. Remember our previous transformation, right? cu1 minus cu2, and then cu1 plus 2cu2. This is from our previous question. You need to look back at the question, right? The question I will write down here. The question here, transformation of v1 v2 v1 v2 equals to v1 minus v2, and then v1 plus 2v2. Okay, so here is cu1 minus cu2, which this is, alright, this is your v1 and v2 alright, and then cu1 plus 2cu2, so this is c1 plus 2cu2. Okay, and when they extract out the c's, so they have u1 minus u2, u1 plus 2u2, and you will get your c multiplied by only you transform the u. Okay, same as before. You can check again using my way, which is quite long, but if you are confused, you can use this way. Alright, you know that you have your u here equals to u1 and u2, so cu is equals to cu1 cu2, and then you transform your cu, you will get your c, alright, cu1 minus cu2, cu1 plus 2cu2. Alright, this is for the multiply first and then you transform. If you transform first tu, transform the u, alright, so you will have u1 minus u2, and then you will have second one is u1 plus 2u2, and then you need to multiply with the scalar, right, c tu, so you will get your c u1 minus u2 u1 plus 2u2. Alright, so you will get your answer cu1 minus cu2 cu1 plus 2cu2. So if you look at the answer here, between these two, cu1 same, cu2 minus cu2, and then cu1 plus 2cu2 plus 2cu2. So it is the same. You can use this method or you can use this method. Either way is correct. It depends on you, okay, how you understand the linear transformation. Both are correct. One is quite longer, but it's easier, right? Because you just compare the transformation of the multiplication with the result of transformation of transform first, and then you multiply. You can compare the result, or you can just try to prove directly. Okay. So for these questions, we know that previously addition is also satisfied, so our multiplication also satisfied. Based from this, we can say that T is a linear transformation. Okay, if one of them linear transformation, if one of them is not satisfied, it's just a mapping. It is not a mapping as a linear transformation. Okay, that's the difference. Before this, before linear transformation, the mapping is just a mapping. But if the equation satisfies both of the addition and multiplication, it is a mapping with linear transformation. It is a linear transformation mapping. Okay. Alright, this slide shows the summary of example 3 and the solution, where this is the solution that they give you for directly proving that it is addition, and this is solution where they give you example of directly proving your multiplication, so that you can use these two methods or the previous method that I explained to you, where we do it one by one and compare the result. Both are correct. You can do both. Alright, so again, for this question, T is a linear transformation because it satisfies both the addition and the multiplication, both. Okay. Okay, now we look at the second definition. Let V and W be vector spaces. The mapping of the transformation of T V to W is called a linear transformation if and only if the transformation of C multiplied by U plus V is equal to C transformation of U plus transformation of V. Okay, this before this we have plus addition and multiplication, right, in the previous definition. Now if you can see, it combined both. We have multiplication here and we also have addition. Okay, this definition show both of them in one equation here, where we have our plus and multiplication. For every choice of U and V in V and scalar C in R. So if V equals to W, then the transformation is also called a linear operator. Alright, we can see the next slide, the example. Alright, so we look at example number 4. We let A be a matrix, n by n matrix, and we define a mapping T Rn to Rm by, okay, this is the transformation of X, Tx equals to the matrix A and X. This is the mapping that they give it to you. Show that T is a linear transformation and let A be 2 by 3 matrix. Now they give you question B here, they give you 2 by 3 matrix. This is A, and find the images of 1, 1, 1 and 7, 81, 5 under the mapping T Rn to Rm with Tx equals to Ax. So they give you the pre-image, right? They want you to find the images. So this is your x. They give you 2 x's. So you need to find transformation of this, what is equals to. Okay, but we know that our Tx is equals to the matrix and x. So x. Alright, this is the mapping that we need to solve. Tx, this is the x, so this is the x. So this is our X, and the results will be the images. Alright, we'll look at the solutions. Here we can say that it is linear transformation based from for all vectors u and v in Rn and all scalar c's in R. We can say that our A C multiplied by u plus v is equals to CAU plus AV. Therefore, our transformation should be the transformation of C multiplied by u plus v is equals to C transformation of u plus T transformation of v. Alright. Since our T, if you look back at our questions, right, the question before, since our Tx is equals to Ax, here, this is the equation that they give us, the transformation that they give us. Since the T is defined by metric multiplication, so in order to solve the question of B, so I mentioned before, this is our x, right? Transformation of x equals to Ax. Right, you need to solve metric multiplication here. So you need to know how to calculate this result to get the answer. Alright? For those who don't know how to calculate this, you need to multiply matrix with x. The matrix with x. So you will get 1 multiplied by 1 plus 2 multiplied by 1 plus -1 multiplied by 1. And then if you calculate, you will get your answer 2. Same here. -1, 1 plus 3, 1, 2, 1. You will get your answer here. Same thing for this. 1, 2, -1, you need to multiply by 7, -1, 5, and you plus them. Same as the second row. So we get your answer for each of the x's. This one and this one. Alright, examples 5 show the general knowledge where most of the common functions studied in calculus are not linear transformation. We have 3 types here, A, B, and C, where we can see that fx equal to sinus x, not linear transformation, because sinus x1 plus x2 is not equal to sinus x1 plus sinus x2. Okay, this is just for your general information. Alright. Fx equal to x2, not a linear transformation, because in general x1 plus x2 squared is not the same as x1 squared plus x2 squared. And fx equals to x plus 1 is not linear transformation, because if you can see here, fx1 plus fx2 is not the same as is equals to x1 plus x2 plus 2, but which is make fx1 plus x2 is not equals to fx1 plus fx2. Okay, because it is not equal, then we can say that most common functions studied in calculus are not linear transformation. Okay, we also have 2 simple linear transformation, which are called zero transformation and identity transformation. How to define this? Okay, if you can see here, transformation of v is equal to 0 for all v. Means everything from v back to v here, if you transform, is equal to 0. Okay, in general, zero transformation is the transformation Rn to Rm that maps every vector in v in Rn to 0 vector in Rm. So every vector in v Rn to 0 vector in Rm. For example, let's say transformation of whatever number you put here, 1, 0, and then after you transform, all of it will be 0. Doesn't matter what number here, it becomes 0 transformation. Second one, transformation of v is equals to v for all v. We call it identity transformation. In general, identity transformation is the transformation Rn to Rn that maps every vector v into itself. For example, you have again here use the same example 1 0. If you do transformation, you will get same 1 0. Alright, same with itself before the transformation. This one, everything's become 0. So we have another two simple linear transformation, 0 and identity transformation. Now we look into the next properties of linear transformation. So we say let T be a linear transformation from V to W where U and V are in the V. Then the following properties are true. Okay, we look at the properties here. If we have a transformation of 0 and after the transformation, all of it should be 0. It cannot be any other number. These are the properties of linear transformation. Okay. Number 2, if you transform a negative vector here, it also equals if you transform the vector and then you add negative after that. It should be the same. Okay. Here actually is the same as if you remember, we have our addition before that. So actually this one is the same, right? So if tu minus v is actually equals to transformation of u minus transformation of v, same as our plus before, right? Addition. Okay, number 4 here, if you can see, this actually is based from our chapter 2, which is linear combination. If you remember, right, we have a scala here for every vector. Okay, so if you transform the vector, so you can have transformation of each of the v1 v2 until vn here with the scalar. So you will get the transformation will be c1, let's say here c1 transformation of v1, c1 transformation of v2 until c1 transformation of cn transformation of vn. Okay, this is the properties of linear transformation that is based on the linear combination that we have learned in chapter 2. Alright, we'll try to see example number 6, which is quite straightforward, where they ask us to determine whether this transformation is a linear transformation or not. So we can use the properties that we know before. So here, since you want to prove whether this is linear transformation or not, they just use the first, I think the t0 equals to 0, right? If the transformation of 0, the end result should be 0. It cannot be other than that. So they try to prove this by entering 0 for x and y, right? And the result is here, the x and y here, 0, and you do your calculator, alright? You calculate using calculator, you will get your result is 1, 1. So we know that the transformation of 0 should be 0, but this is not equal to 0. You have 1, 1, you have value here other than 0. So we can say that we know that T is not a linear transformation based from these properties of linear transformation that we have just proved. Okay, now we look into example number 7. I think this is a straightforward example where they ask us to show the mapping whether it is a linear transformation, this mapping here. So we use this is the plus, right, that we learned in example number 3, number 4, right? And this is our multiplications, and we can say that the TAB is actually equals to transformation of A plus transformation of B, whereby the transformation of C multiplied by A is equals to C multiplied of transformation of A. We can see directly. So thus we can say that T here is a linear transformation because of it satisfies these two properties. Okay, the null space, kernel and range. So if T transformation of V to W is a linear transformation, then the set of vectors in V that the transformation maps into 0 is called kernel or null space. And the V here is in V, alright? When it transform, it will show 0. For example, we have here W, this is V, and when in map, it will show 0. Okay, so the kernel is in V, alright, not in W. But for range is the set of all vectors in W that are images under the transformation of at least one vector in V that is called the range of the transformation. So for range, we have the V, so we have here W. So we have and when you map V, it will show into this space in W where it is called a range. Remember, for range, it is in W. When you transform the V, right, it will be in this range. But for kernel, if you transform the V, it is in the V here. Alright, kernel is in here. When it transform, it will show 0 in the W. Alright, again, this further illustrate what the point I'm making before. But now it's V and W, V and U, right? So here, see, null space is in the V, right? Is in V. When you transform it, it will show 0. Any vector in this V. But for range, anything in V here, right, that be transformed into this space here in W. Okay, so the range is in W. Oh, sorry, for this case U. For null space, it's in the V. Alright, remember, null space in V, range is in U. Let's look at the next example, example number 9. They ask us to find the kernel of linear transformation, and the transformation from R2 to R3 represented by this equation here. Alright, this is the transformation, and this is the is equals to. And then to find the kernel, we know already that for kernel, have our V, let's say W, B and W. So we know that any vector here from V, it will points to 0. Okay, so basically in the W it will be 0. So to find the kernel, you need to write this solution here from the equation that we have that they give to us. This is depend on the question. Sometimes they give you different type of equation, so the difficulty will depends on the equation itself. And then it is equals to 0. After the transformation, this should be 0, 0, 0, because we know that for kernel, if we transform it, it will be 0 on the W. Okay, so we have this is our first linear here, second linear and third linear. So we know that already we will got a homogeneous system where x1 minus 2x2 is equals to 0, and the second one is already 0. Alright, so the third one, negative x1 is equals to 0. So you solve this linear equation, right? And then you will get the solution here, where trivial solution, x1 here is 0 and x2 also is 0. So we will have the kernel equals to 0 and 0 to get our W here. Okay, we look at example 10 here. Define the linear transformation from R4 to R3 by, this is transformation here. Alright, find a basis for the null space of T and its dimension. So we know already how to find a basis for null space. Okay, look back at chapter 3. Okay, this is based from our chapter 3, finding the basis for null space. Alright, how you find a null space. So we must, here, the one is new here, so we must know for finding a null space must equals to 0. Okay, that's how you can find the null space and its dimension. You find the basis first, and based from the basis you will get the dimension. You need to look back at our chapter 3. So we will have a plus b equal to 0, b minus c equals to 0, a plus d equals to 0. Alright. Same as we did previously, the null space found by setting each component of the image vector is equals to 0, which we have did in the last slides. So we will have a linear system, alright, that have infinitely many solutions given by. This is what you get after you do the solving the linear equation. So in case you forget, alright, so we have A, B right here. So we have A, B, C, and D. So we have 4, right? So the first one here we have A plus B, this one B negative 1, so B negative 1, and then we have A. Solve this, alright, solve this, and then you will find your answer as here, where we get our t that belongs to a real number. We get your solutions. I will not explain much more about this. I think you already understand by looking back at chapter 3. Okay, hence if you bring out the t, okay, so you get your negative 1 1 1 1. So this is a basis that consists of one vector. So this is your basis, alright. If you bring out the t from previously, and then of course the dimension is how much is the basis, so the dimension is 1. This is all from your previous chapters. Okay, look at this theorem here. We will have VW be a finite dimensional vector space where B here equals V1 until Vn be a basis of V. If the transformation of V towards W here is a linear transformation, then the range here, range of the transformation is a span of the transformation of V1, V2 until Vn. Okay, this is a theorem that we need to know for the calculation of our range. Alright, let's look at the next example, example 11. Where let the transformation from R3 to R3 be a linear operator and B is equals to V1, V2 and V3, a basis for R3. So suppose that they give us the transformation of V1, V2 and V3. They ask us two questions. Alright, is W121 in range of the transformation? And B, find a basis for R3. Okay, actually these questions combine two things. This is from range of transformation, which is in this chapter, but finding a basis is from our chapter 3. Okay, so actually they want us to find, as mentioned before, this is our V, this is our W. They want to find what either 1 to 1 here is in this space in W after the transformation. Okay, so is 1 to 1 in this W, so we must find here, we must find the V here. Okay, so transformation of V W equals to 1 to 1. So is there a V here? They give us the W after the transformation, which is 1 to 1. So they want to know, is W in a range? So we must find the V. Okay, for this question they ask us to find a V for W 1 to 1 is the range of the transformation or not. Okay, that's what this question wants for A. Okay, we try to solve it. Alright, so now we know what they give us and what they don't give us. They give us the W, which is the 1 to 1 here, and then they give us this 3 TV1, TV2 and TV3. So if you remember, we have our fourth properties, right? The linear combination where V is equals to V1, V1. This is also in chapter 2, right? In the previous chapter. So you know the theme here, you need to understand chapter 2 and 3 first. Then you can go for chapter 4. Okay, C2, C2, V2 plus C3, V3. Alright, this is from the fourth theorem. So we also know that the transformation of V is equals to C1 TV1, C1 transformation of V1 plus C2 transformation of V2 plus C3 transformation of V3. Okay, we know that after transformation of TV we will have our W, which is 1 to 1. We need to find the V, okay, before the transformation. Alright, after transformation we get the W, which is 1 to 1, and then we don't know our C1, but we know our all of our transformation of V1, V2, V3, which they give to us here. So we know this is 1, 1, 0 plus C2 1, 0, 1 plus C3 2, 1, 81. Alright, so we need to solve this equation in order to find our C. If we find a value for our scalar here, the C, then we can say we can find the range. Then it is in RT. Okay, the range. But if you cannot find the value for C, then it is not a range. Alright, let's look at how to answer this. Okay, again, based from previous slides, we already identify the scalar. I mean, identify the theorem we want to use here, the properties number 4, where we have our C transformation V1 until V3, and then we have our W here. So we make into the equation where we need to solve this in equation 1, 1, 2, 1, 1, 0, 1, 2, 0, negative 1, negative 1, 1. Solve this. Alright, this is your previous chapters. When you solve it, you must find the scalar here. If you find a value, then we can say that it is belong to the range. If you do not find the value, it does not belong to the range. Right, after you solve the linear system in previous slides, for this problem you will get the answer like this. Alright, again, this is all based from our previous chapters. If you don't understand this, you need to look back in our previous chapters. Okay, after you get the solutions of the linear system, you can see we have many solutions, and this is one of the solution that we can have. Alright, so we can see we have the value for each of the scalar in our linear combination. So we can say W belongs to the range. What if we cannot find a value for one of them here, the scalar here? If we don't have a value, then we can say this W not in R transformation. Okay, don't be confused. If you have a value, so for the example we have a value, right, for the linear system. So in this case we have many. Alright, so they say if t is equals to 0, So this will be the value for each of our scalar C1, C2 and C3. So we can say W belongs to the range, but if we don't have a solution, we write thus W do not belong to the range. Okay, so the question depends on chapter 3. Many of things you do here depends on chapter 3, where you need to know how to solve the linear system, alright, until you get this solution, and then you will find your answer. Okay, and I hope you can interpret it well. Alright, for question B, it is actually not from this chapter. Question B here is from our chapter 3, where you need to find the basis. Alright, so find the leading ones here. We have 2, right? Again, I will just simplify it because this is chapter 3, you should know already. So the leading ones, column 1 and 2, and the basis for the range is given by a span of 1, 1, 0, 1, 0, negative 1. Observe that since the range is spanned by two linearly independent vectors, RT range is a plane in R3. So basically you get your answer. But this is all you learn in chapter 3. Okay.